Hello, everybody. Welcome back. I hope you like my spooky decor. It's Halloween week, so I thought I would be festive. Anyway, today we're going to be talking about Unit 4.9, which just goes into a little bit more detail on redox reactions, and this is the last subunit in Unit 4, so let's get started. All right, so if you will recall, what makes something a redox reaction is when electrons are transferred in a reaction. So we see one element losing electrons, we see another element gaining electrons. And again, how do you know that? Because you would assign oxidation states above each element and look at what's happening to it from left to right, from reactants to products. And what we're going to, let's just look at a quick example here in front of us. If I were to assign oxidation states above each element, let's just review. Zinc by itself has an oxidation state of 0. This one's easy because the charge is written right next to it. Same here. Okay, so let's take each element individually. Zinc is going from 0 to +2. Its charge from left to right is increasing. That is oxidation. Zinc has been oxidized where the iron has been reduced. I can see that because its charge has decreased. So in a lot of redox situations, you'll simply be asked which element is oxidized, which element is reduced. How do you know? You describe what is happening to the oxidation state. But what we're going to talk about today is how to balance a redox reaction. Okay, and the way that you do that, and what I'm going to do, guys, is I'm going to just, if I were to pull up everything on this slide, you would see a series of steps. Okay, I'm actually just going to work through this example and then I'll show you the steps in just a moment. The first thing that you need to do when you're asked to balance a redox reaction, which is not the same as balancing a regular reaction, the first thing you need to do is write what are called half reactions. Okay, now if you look up at that example, you might say, well, that looks balanced to me. All the elements are balanced, and you're right, but redox reactions are unique because they are not charge balanced, and that's the thing. So I'm going to write two separate reactions, one for the reduction and one for the oxidation, and I'm just going to start with the zinc. Okay, zinc looks like that on the left, and zinc looks like this on the right. And I'm not going to change it in any way. I didn't rewrite those elements in any way other than the way they were presented in the reaction. Okay. The other half reaction, of course, is the iron, and it looks like this. Okay, so I've written out my two half reactions. The next thing that I'm going to do is I am going to balance each equation, each half reaction, for charge, and the way that you do that is by adding electrons to one side. Remember, guys, electrons are negatively charged. All right, so let's start with the zinc reaction. Zinc has a charge of 0 on the left and +2 on the right. To make those charges equal, I'm going to add 2 electrons on the right. Okay, let's look at the iron reaction. It's +3 on the left and +2 on the right. If I'm going to add some number of electrons to one side, I'm going to add it to the left side, and I only have to add 1. One thing to take stock of at this point, ladies and gentlemen, is that make sure that your electrons are on opposite sides. If you find that in one reaction you've got it on the reactant side and the other one it's on the electrons are on the same side, you've done something wrong. Stop and start over. But this looks good to me because the electrons are on opposite sides. However, they don't have the same coefficient. And they have to, okay? Because eventually I'm going to be adding these reactions together and the electrons must cancel out. So in order to make the electrons have the same coefficient, I can't just put the number 2 there, okay? I'm going to multiply this entire equation times 2. All right, and if I do that, then I get this. Okay. And at this point then, I'm going to erase this just so I don't get confused because I don't need this one anymore. Okay, so these are my 2 balanced half reactions, and I am now ready to add them together. Remember, anything that's the same on opposite sides of the arrows, I can cancel out. So here is my final balanced equation. And the order in which you write your reactants and products doesn't matter. Okay, final answer. So not only are the elements balanced, but the charges are balanced as well. If you'll notice, both sides of the arrow have an overall charge of +6. So this is not only charge balanced, it's element balanced, and you want to always check that at the end. Okay, so let's review what we just did. We wrote out separate half reactions. We balanced the charge, adding electrons to one side. If necessary, and it was in that case, we multiplied one of the equations by the number 2 to equalize the electron count. We added them together, and we made sure that all the elements and charges were balanced. So that's the process on balancing a redox reaction. Okay. So let's just do one more together, and then I'm going to give you one to practice on your own. It says the half reactions for the oxidation-reduction reaction between chromium and silver ion are represented above. Letter A says which substance is being oxidized and which substance is being reduced. So let's assign oxidation states. This is 0, this is +3, this is +1, and this is 0. So if you look at chromium first, chromium's charge has gone from 0 to +3. That is oxidation. Silver has gone from +1 to 0. That means it has been reduced. Okay. Then it says write the balanced net ionic equation for this reaction based on those half reactions. So that's actually very nice. They've already written the reactions out for us. So the electrons are already written in. I can see that they're on opposite sides of the arrow. They should be. What's the only problem? The electron count is not the same. So what am I going to do? I'm going to multiply that silver equation, the whole equation, times 3. And then if I were going to add them together, the electrons are going to cancel out. And you're going to write everything that remains. And if we do that, we end up with this. And let's verify, yep, the elements all look balanced. And each side of the arrow has an overall charge of +3. So that checks out. So I want you to try this one on your own. It's very similar. So I want you to pause the video and see how you do. All right, let's check it. So in this case, cobalt is the element that was oxidized, silver was reduced, and there is your balanced equation. The only thing else that I really want to say is, let's just say, and I know this doesn't make sense, but let's say for whatever reason, silver had a +3 charge, which means that there would be a 3 there, okay? Look at these coefficients here. There's 2 electrons in the cobalt equation and 3 in the other. Think about what you would have to do to get those 2 equations to add so that the electrons cancel. I would have to multiply this whole equation times 3 and this whole equation times 2. It doesn't come up very often, but it could. Okay, so just think about, you know, what do you have to multiply one or both equations by to get them to equal the same number? That does come up on occasion. So that concludes Unit 4, and I hope that you've learned a little something, and I hope you enjoy the festive decor, and I look forward to seeing you next time.